Okay, so in this assignment, what you'll be doing is given an array of integers, you want to find this three element tuples, say I, j, k, such that they add to a target sum. So, for example, if the target sum is 20, for given an array, you want to find any three integers that will add up to 20. Now, so for example, if 4, 6, 10 are the three integers that add up to 20 and they exist in the array. Now, depending on your logic, you could come up with identifying more than one among these tuples. You see, all the 6 or different combinations of the three element tuple 4, 6 and 10. So it will be like 4, 6, 10 or 4, 10, 6, 10, 4, 6, 10, 6, 4, 6, 4, 10, 6, 10, 4. So all these things are the same three elements put together in different order. So a brute force approach, the code for which I have already given you. So here you are creating a random array and filling it in this array, and going through a nested loop, an I loop, j loop, k loop to identify the three elements at different indexes. So running say I from 0 to num elements minus 1, and num elements is the number of elements in the array. J runs from I plus 1 to num elements minus 1, and k runs from j plus 1 to num elements minus 1. So they are guaranteed to find the three elements at three different indexes. Now there are two inefficiencies here. One is like, okay, you're checking if the sum of the three elements at indexes I, j and k add up to target sum. If so, that's counted as one occurrence of I, j, k. You could print it if you want to. And then you're continuing the k loop. Now, it is possible that you could find out some other three elements or 4, 6. So it is possible that you will find some other combinations of three elements that will add up to target sum by continuing the k loop, because this is an arbitrary array. So if it's an arbitrary array, this is probably the best approach to find the three element tuples that will add up to a target sum. But you see there are a lot of redundancies that are possible if the array is arbitrary and you run through such a brute force approach. So that's why in this assignment I suggest you to sort the array and then perform this search process, which I called as an improved search. So as I'm creating the array, I'm also creating another array called sorted array, which is not yet sorted. I'm just going to fill the same values that get into the array. So both array and sorted array have the same set of values. And then after I fill the array, I call the insertion sort algorithm, the code for which is already given here, to sort the sorted array. So by the time you come out of this insertion sort, the sorted array is actually sorted. Now, in terms of the basic operation, the number of comparisons is what we are going to look at. So comparing the sum of array of I, j, k with target sum is a comparison, and that's what I'm adding here for the brute force search. So with your improved search, you're going to again do some comparisons. And as you can see, the sorting is a kind of overhead for the improved search, because you want to get the array sorted first and then perform an improved search. So the number of comparisons involved in sorting needs to be accounted for. And then I have given the space for you to implement your improved search algorithm on this sorted array. So if the array is sorted, it is possible that you can minimize the number of it's definitely possible to minimize the number of comparisons you will do for the sum of the elements at index I, j, k with target sum. Okay, so I want you to come up with that logic to minimize the number of comparisons. to search for a 3-element tuple that add to a target sum in a sorted array. Now, there's one other inefficiency here, which is the number of additions. So you can see here in the brute force code, I'm adding array of I plus array of j, which really comes from this first loop and second loop. So once you get inside the k loop, I and j are fixed. So instead of adding array of I and array of j every time inside the k loop, you could actually bring in that sum to the k loop and just add that sum to the array of k. You could start from here and store array of I in a variable and then add it up with array of j and store it in a sum and bring that sum to this k loop, and that will significantly reduce the number of additions you do. And that's the other improvement I want you to incorporate in your improved search algorithm. So now one last thing is, so what are the possible target sum values you will run this code for? So you are creating, if you look at the logic I have here, you're creating the array only once, and the sorted array also has the same elements to begin with, and then it gets sorted. And I run a loop for the target sum. You see, the maximum value for any element in the array can be max value. So given that, and you want to find a 3-element tuple, the maximum value for the sum of all the 3 elements at index I, j, k could be 3 times the max value, and it cannot be beyond that. So I'm running my target sum loop from max value to 3 times max value and incrementing target sum by 1. So for each value of this target sum, the loop index itself is the target sum, you are going to run a brute force search to find all the 3-element tuples that add up to the particular target sum, as well as run your improved search to determine all the 3-element tuples that add up to the target sum. Okay, so I can also here improve to identify all the 3-element tuples that add up to the particular target sum. So the number of comparisons is measured for each target sum. So you see it is initialized to 0 for the brute force, as well as the number of additions is accounted for each target sum. Similarly, the number of comparisons and additions with the improved search is also measured for each target sum variable, each target sum value. So the input parameters to this code are the number of elements and max value. So at the end of, after you implement your improved search, you see you are printing here the target sum, and for that particular target sum, the number of comparisons encountered with the brute force approach, and the number of comparisons with the improved search that will include the sorting related comparisons, the number of additions for the brute force, and the number of additions with the improved search. So I have implemented that based on the improved search based on sorting, and I test ran my code for the array size of 100 elements and the maximum value being 25 for any element, and this will be the 5-element output we get. The target sum value, the number of comparisons with the brute force search, which doesn't change because you're not really doing any optimization there, and this is the number of comparisons with the improved search, with, as I said, is expected to basically increase with the target sum, and number of additions with the brute force approach, which again, as I said, there's no optimization there, and this is the number of additions with your improved search, which is again expected to increase with increase in target sum. So if you kind of really plot things, this is what I got for 100 and 25, 100 elements and 25 is the max value. And target sum will then range from max value to 3 times max value, so it will be like from 25 to 75. And you can see the blue line is the number of comparisons with the brute force search, and the pink one is the number of comparisons with the improved search. It is kind of lower than that with the brute force search, and it's approaching, and eventually it gets closer to it, and some a little bit larger than the number of comparisons with the brute force search. So, as I said, it doesn't make sense to have target sum more than 3 times the max value, because you're going to identify only 3 element tuples. So you can see only when it is even more than twice the max value, like it's about even like more than 2.5 times the max value, it is starting to be above the number of comparisons with the brute force search. So that's why I said your objective in this improved search algorithm is try to reduce the redundancy as low as possible. So you cannot completely avoid. So if 4, 6, 10 are the 3 elements that add up to 20, which is the target sum, then you cannot completely avoid or you cannot completely have just one of the 6 combinations. It could, depending on your logic, you could identify more than one of these 6 combinations for 3 elements like this. But you try to reduce as much as possible the redundancy, and the more effective is your strategy in trying to reduce the redundancy, the lower will be the number of comparisons. And this is for the number of additions. You can see this, the blue line again with the improved with the brute force search, and the pink one is with the improved search. So the number of additions is definitely getting much lower with the improved search algorithm all the way till the end. And where it tries to kind of get saturated and becomes a constant, that's the point actually. I think you could also notice here the number of comparisons getting above the number of comparisons with the improved search getting above the number of comparisons with the brute force search. Like when I say above, it's not much larger, it's very little bit ahead. Okay, so it doesn't go much above the brute force search, and that's what I would expect your improvement also to be. It should not go much larger than that with the brute force search. So I have assigned the n and m values, the number of elements and the max value for each student, and you will work on when you show me the sample output and the screenshot, the plot and everything, you will show for the n and m values assigned to you. And so as part of the submission, you'll submit the entire code. So this what I'll give you is a startup code, a student version. So you'll implement your input search algorithm here and submit the whole file, the CPP file, and then a PDF file, one PDF file that includes everything that is listed here. So it includes all the things like the Excel plot, the sample output, everything. Okay. So again, this is one scenario example sample execution I have included here. For this given arbitrary array, it should be yeah, this should be 1 second. Yeah, so if you run the brute force search on the arbitrary array which is not sorted, if the target sum is 20, these are the 3 element tuples that add up to 20, and these are the indexes at which they are occurring. So it is possible that you can see this 4, 10, 6 gets repeated here, and then as 10, 4, 6 and 4, 10, 6. So that's the kind of redundancy I would like to reduce as much as possible. So if you get sorted, the 4106 is appearing as 4610 only a couple of times. This 6311 is appearing here, 3611, and 4412, 412, 4, and yeah, so it's appearing as 4412. So you notice that you are not losing any of the 3-element tuples. So that's another important thing you have to accomplish as part of improved search. You should not miss any of the 3-element tuples. So 4610 is captured here, and then 4124 is captured here, and then 6311 is captured here. So you should not be losing any of the 3-element tuples. Again, I could not, with my strategy, I could not avoid this 4610 appearing appearing twice. So that's why I said you cannot reduce it, you cannot totally avoid the redundancy. So your target is to reduce the redundancy as much as possible. Okay, with that I'll finish this video.